This question asks you to identify true statements about the Matern kernel, a function used in Gaussian process regression, when the smoothness parameter, nu, is set to 2.5. We'll explore the properties of this kernel to find the correct answers. Let's dive in. This statement claims that the Matern kernel with nu equals 2.5 can be differentiated an infinite number of times. I'll explain that this is incorrect. Only when nu approaches infinity does the Matern kernel become infinitely differentiable. It approximates a Gaussian kernel. For nu equals 2.5, the Matern kernel is only twice differentiable. Think of it like this. A straight line is infinitely differentiable, but a curve with sharp corners is not. This statement is correct. The Matern kernel has a parameter called length_scale. This parameter controls how quickly the correlation between data points decreases as the distance between them increases. A smaller length_scale means correlations decay rapidly. Points far apart are less correlated. A larger length_scale means correlations decay more slowly. Points far apart may still be strongly correlated. Correct again. The computational cost increases with nu due to the complexity of calculations required. Because 2.5 is greater than 1.5, the calculations for the Matern kernel with nu equals 2.5 are more complex, hence more computationally expensive. This statement is false. Setting the length_scale to 0 creates problems. It makes the kernel matrix singular, or non-positive definite, which means you can't use standard Gaussian process techniques. The calculations simply break down. The nu parameter dictates the smoothness of the Matern kernel. Larger nu values lead to smoother functions. Think of it like drawing a line. A larger nu value is like using a smoother pen, while a smaller nu value is like a more jagged pen stroke. The length_scale is another important parameter. It determines how quickly the correlation between points decreases as their distance increases. A smaller length_scale means correlation decays faster, and a larger length_scale means it decays more slowly. I'm going to this one. The Matern kernel with isn't infinitely differentiable. Only when nu approaches infinity does it become infinitely differentiable, and it essentially becomes a Gaussian kernel. Think of it like this. Higher nu values mean more smoothness, but even still has limits. This one's. A larger nu value makes the calculations for the Matern kernel more complex. It's like baking a cake. A more elaborate recipe, higher nu, takes more time and effort. Absolutely. The lengthscale parameter is crucial. It defines how quickly the correlation between data points decreases with distance. A smaller lengthscale means rapid changes in the function's behavior, less smooth, whereas a larger lengthscale implies smoother variations. I'd mark this as, setting lengthscale to 0 will make the kernel matrix singular, or non-positive definite. This will cause big problems in the Gaussian process calculations. It's like trying to divide by 0. It just won't work. This is a multiple-choice question testing my understanding of the Matern kernel in Gaussian process regression, specifically focusing on the impact of the nu and length_scale parameters. I need to identify which statements about the Matern kernel with nu equals 2.5 are true. This statement is false. I know the Matern kernel with nu equals 2.5 is only twice differentiable, not infinitely differentiable. Only when nu approaches infinity does the Matern kernel become infinitely differentiable, approaching a Gaussian kernel. This statement is true. The length_scale parameter is a fundamental part of the Matern kernel, influencing how smoothly the function behaves. A larger length_scale means the function changes more gradually, whereas a smaller length_scale implies more rapid changes. This statement is also true. Higher values of nu generally mean the kernel calculations become more complex, leading to higher computational cost. So, nu equals 2.5 is more computationally expensive than nu equals 1.5. This statement is false. Setting length_scale to 0 is problematic because it makes the kernel matrix singular, leading to computational errors in the Gaussian process estimation. I'll explain the Matern kernel, a crucial component in Gaussian process regression. It's a function that measures the similarity between data points, influencing how smoothly the model interpolates between them. Understanding its parameters is key to using it effectively. This question tests your knowledge of the Matern kernel's properties, particularly when the smoothness parameter, nu, pronounced nu, is set to 2.5. We'll evaluate each statement individually. This statement is incorrect. A Matern kernel with nu equals 2.5 is twice differentiable, not infinitely so. Only when nu approaches infinity does the Matern kernel become infinitely differentiable, approaching a Gaussian kernel. Think of it like this: a higher nu means a smoother function. An infinitely differentiable function is super smooth. This is correct. The length scale parameter determines how quickly the correlation between data points decays with distance. A shorter length scale means nearby points are more strongly correlated, leading to a less smooth function. It plays a major role in controlling the output's smoothness. This statement is also correct. Generally, a higher nu value increases the computational cost. This happens because higher nu values result in more complex calculations when the kernel function is evaluated. This is incorrect. A length scale of 0 causes issues. It essentially means that there's no spatial correlation, leading to a singular kernel matrix. A singular matrix is bad news. It often means the model is unable to find a solution. It leads to errors during calculations. This describes the properties of the Matern kernel, a function used in Gaussian process regression, specifically when its smoothness parameter, nu, is set to 2.5. We'll explore what this means for its differentiability, computational cost, and the effect of its length scale parameter. This statement is true. The Matern kernel has a parameter called length_scale. This parameter essentially dictates how quickly the correlation between data points decreases with distance. A smaller length scale means correlations drop off quickly. Points further apart are less related. A larger length scale has the opposite effect. This directly influences the smoothness of the resulting function. This is also true. Higher values of the nu parameter in the Matern kernel increase the complexity of its calculations, resulting in higher computational costs. Think of it like this: a smoother curve, higher nu, requires more calculations to define than a rougher curve, lower nu. I found this statement to be false. While a higher nu does imply more smoothness, it doesn't reach infinite differentiability. Only when nu approaches infinity does the Matern kernel approach a Gaussian kernel, which is infinitely differentiable. With nu equals 2.5, the function is only twice differentiable. This statement is false. Setting the length scale to 0 causes problems. It leads to a singular kernel matrix. This means you can't solve the equations involved in Gaussian process regression. It's like trying to divide by 0, it's undefined. I'm asking you to identify which statements about the Matern kernel, a specific function used in machine learning, are correct. We'll focus on the implications of setting the nu parameter to 2.5. Let's dive in. This statement is false. The Matern kernel width is only twice differentiable, not infinitely differentiable. Think of it like this: you can take the derivative twice, but after that you won't be able to define it anymore. Only when approaches infinity does the Matern kernel become infinitely differentiable, approaching a Gaussian kernel. This statement is true. The Matern kernel has a parameter called. This parameter determines the typical distance over which the function changes significantly. A smaller length scale means the function changes rapidly, less smooth, while a larger length scale makes it change slower, smoother. It's kind of like zooming in or out of a graph. This is also true. As you increase in the Matern kernel, the calculations involved become more complex. It's like solving a more intricate puzzle. It takes longer to solve. That means that using takes more computational time than using because the math is more difficult for the computer. This statement is false. Setting to 0 creates problems because the resulting kernel matrix will be singular, making the calculations unreliable. Imagine trying to build a house with a completely missing support beam. The whole thing would collapse, right? I'm focusing on understanding the Matern kernel, a function used in Gaussian process regression, GPR. It's a powerful tool for modeling relationships in data, and its properties are controlled by parameters like nu and lengthscale. This question tests your understanding of how these parameters impact the kernel's behavior. Setting the lengthscale parameter to 0 is a big no-no. It creates a singular, non-positive definite kernel matrix. This makes the mathematical calculations in GPR break down. Think of it like trying to divide by 0, it just doesn't work. A valid kernel matrix is essential for the GPR model to work correctly. That's incorrect. A Matern kernel with nu equals 2.5 is only twice differentiable. Infinite differentiability only happens when nu approaches infinity. This is absolutely true. The lengthscale parameter directly affects how smooth the function appears. A larger lengthscale will lead to a smoother function. Yes, this is correct. The computational cost increases with the nu value. Higher nu values mean more complex calculations, leading to longer computation times. This is the core question that tests your understanding of the Matern kernel's properties, specifically when nu equals 2.5. The statements following this question will test your knowledge of this particular kernel function.